Something ended decades ago, and almost nobody noticed. Not with fire, not with a flash, not with any of the drama you'd expect from what might be the single biggest event in the story of intelligent life in this galaxy. It ended in silence, and we are still sitting inside that silence right now, mistaking it for an empty room. But in a small laboratory in Cambridge, Massachusetts, a physicist once did something to a beam of light so strange, so quiet, so easy to miss if you weren't looking closely, that it changes what the silence out there might actually mean. Once you hear what she did, you may never look at a clear night sky the same way again. Here's why that's worth 10 minutes of your time. In a moment, you're going to learn how a scientist trapped a beam of light inside a cloud of atoms colder than deep space, held it completely still, turned it into matter, carried that matter across a gap, and turned it back into light again on the other side, whole, undamaged, exactly as it had gone in. That part alone is one of the strangest verified results in modern physics. But it's what that discovery quietly implies about 60 years of cosmic silence that is the part almost nobody connects. Stories like this one live in the space where hard physics and honest wonder overlap. The kind of place where a real, published, peer-reviewed result turns out to be stranger than anything you could invent. If that's the kind of place you like spending time, you're in good company here, so settle in. And if by the end you find yourself wanting more of this kind of slow, careful, wait, that's actually true storytelling, the subscribe button is sitting right there, and it genuinely helps this reach more people who'd enjoy it too. For now, let's go back to where this really begins, long before any laboratory, with a question almost everyone eventually asks while looking up at a clear night sky. There are somewhere between 100 and 400 billion stars in the Milky Way alone, and modern surveys suggest a meaningful fraction of them carry planets sitting in the narrow zone where liquid water can exist on a surface, in orbit stable enough to have held steady for longer than life has existed here on Earth. That isn't a hopeful guess dressed up as science. It's measured, cataloged, published, argued over in journals, and mostly agreed on. By the numbers alone, the universe should not be quiet. It should be humming, at least a little, with something. Instead, for more than 60 years, radio telescopes pointed at the sky in every direction astronomers can think to check have logged an almost unbroken silence. Billions of frequency channels swept, cross-checked, swept again. Nothing that reads back as a voice. This is usually called the Fermi paradox, after the physicist said to have asked a version of a very simple, very unwelcome question over lunch one afternoon. Where is everybody? It's a completely fair question, but most retellings of it skip a detail that turns out to matter enormously. And that detail doesn't start with a telescope. It starts with a basement laboratory in Cambridge, Massachusetts, in the final years of the 20th century, where a physicist did something to a beam of light that nobody had ever managed before. Something that quietly rewrites what the words signal and silence even mean. Picture this for a second. A pulse of light, the fastest thing the universe permits to exist, slowing down and down and down until it's moving slower than you could comfortably pedal a bicycle. Does that sound like a magic trick to you? It isn't. It's recorded. It's peer-reviewed. It happened in a real room, under lights that hummed the way old laboratory lights do. And it happened because one physicist refused to accept that the speed of light was as fixed as everyone assumed. The physicist at the center of this story is the Danish-born Lene Howe, who by the late 1990s was working out of the Roland Institute for Science in Cambridge, Massachusetts, later continuing the work at Harvard University. Even some of her fellow physicists doubted the whole premise of what she was attempting. As she later recalled, colleagues would ask her why she'd even try these experiments, insisting it wouldn't work right. She tried anyway. In 1994, her team built an unassuming piece of equipment they nicknamed the candlestick, a small chamber that heated molten sodium metal just enough to release a thin stream of vapor upward, feeding a cloud of atoms into a trap built from precisely tuned magnetic fields and laser light. Those lasers didn't just hold the atoms in place, They stripped away the atom's motion, photon by photon, cooling the cloud down to somewhere around 50 billionths of a degree above absolute zero, a temperature that, as far as anyone knows, doesn't occur naturally anywhere else in the observable universe. At that temperature, something genuinely strange takes over. The atoms stop behaving like a crowd of separate individuals and start behaving like one single object. Their quantum wave functions overlap, then merge, until millions of atoms occupy the same lowest energy state at once, a phenomenon predicted mathematically back in 1924 and not actually produced in a laboratory until 1995. Physicists call it a Bose-Einstein condensate. It is, by most measures, the quietest, stillest matter that has ever existed on the surface of this planet. And it turns out that inside that stillness, you can do something to light that shouldn't, by ordinary intuition, be possible at all. Normally, when a beam of light hits a cloud of sodium atoms, the atoms absorb it almost instantly, and the gas turns opaque, the way fog swallows a flashlight beam a few feet in. But shine a second precisely tuned laser into the condensate at the same moment, and the physics shifts under your feet. That second beam sets up a quantum interference effect, one that cancels out the very process that would normally absorb the first beam, and the cloud that was opaque a moment earlier becomes transparent to it. This effect has a name: electromagnetically induced transparency. And it does something else at the exact same time. It drags the group velocity of that first beam of light down and down and down. In February of 1999, Howe and her collaborators published the result on the cover of the journal Nature. A beam of light, slowed from its usual 299,792 kilometers per second down to about 17 meters per second, a brisk bicycle ride. The number made headlines around the world, but the real discovery sitting underneath the headline was quieter and stranger than most of the coverage let on. The speed of light, it turns out, is not some fixed, unchangeable property belonging to light itself. It is a property of the relationship between light and whatever medium it happens to be moving through. Engineer that medium precisely enough, and you can engineer the speed. Slow it, compress it, a pulse that would ordinarily stretch a mile or two through open space, folding down into something smaller than the width of a human hair. And then, 2 years later, in 2001, Howe's team went further still. They found a way to switch that second laser off entirely while the pulse of light was still traveling inside the condensate. The pulse had nowhere left to go. It stopped completely. Its entire structure, every bit of information it carried, imprinted directly onto the shared quantum state of the atoms holding it, sitting there, waiting until the second laser switched back on and the light walked back out into the world exactly as it had gone in, undiminished. Stop for a moment and actually sit with that. Light stopped. Not slowed to a crawl, stopped, held, and released again, unharmed, on command, inside a cloud of atoms you could hold in your cupped hands. If you can do that to the single fastest thing the universe allows to exist, the question worth asking isn't whether it's a neat trick. It's what else might be possible that nobody has thought to try yet. What Howe had actually built, without the full implications being obvious at first, was a working form of quantum memory. And a laboratory that can write information onto a beam of light, freeze that information in place, and read it back out again later, isn't just performing an elegant trick for physics documentaries. It's chipping away at one of the hardest open problems in the entire field of quantum communication. Here's why that problem matters so much. Any signal sent across real distance runs into the same enemy every communications engineer fights daily: noise. Cosmic background radiation, stellar interference, the ordinary decay of a classical signal as it spreads out and thins across empty space. A classical signal, the kind of radio wave SETI has been listening for since the first organized search began in 1960, gets weaker and messier the farther it travels. And eventually, something has to catch it, clean it up, and boost it back to strength. Quantum information doesn't play by those rules. A quantum state encoded onto a single photon can't be copied partway through the journey without destroying it, can't be secretly read without disturbing it, and can't be amplified by an ordinary repeater the way a classical signal can. These aren't engineering limitations waiting on a clever fix somewhere down the road. They're theorems written directly into the mathematics of quantum mechanics itself, about as close to an unbreakable rule as physics offers. Which means that if you want to move quantum information across any real distance, you need a device that can catch it, hold it as a physical object instead of a fleeting pulse of light, and release it again exactly as it was on command. In effect, you need something very close to what Howe's laboratory had already built. So in 2007, her team published a further result in Nature. They stopped a pulse of light inside one condensate, converted its information into a physical excitation, a matter wave, and let that matter wave travel on its own through real space into a second, entirely separate cloud of atoms about 0.2 of a millimeter away. Once there, a second laser triggered the atom's memory of the original pulse, and it reappeared, reconstructed in that second cloud. Howe herself later described the result plainly. The team had, in her words, managed to reincarnate the pulse in another cloud 0.2 of a millimeter away, restored whole. The information had crossed that gap as matter, not as light, not as anything resembling an ordinary transmission, and it arrived intact on the other side. 0.2 of a millimeter is nothing next to a light year, and it would be dishonest to pretend otherwise. But here's what changes everything about how you should think about the story of the silent sky. Physics doesn't care about scale, only about principle. What Howe's lab demonstrated, piece by piece, across roughly 13 years of published, reproducible work, is the core building block of what engineers call a quantum repeater, which is, in turn, the missing piece required for anything resembling a genuine, functioning quantum internet. Now think for a moment about what a civilization would actually do once it had fully mastered a technology like that, scaled up over centuries instead of over a single career. A species running mature quantum communication has very little reason to shout into the void the way humanity still does. Broadcasting, the way 20th century humans figured out how to with radio, is wasteful and indiscriminate by design. It's the kind of thing you resort to when you don't yet have a better option, which is, not coincidentally, exactly where humanity currently stands. We've been sending electromagnetic signals out into space for roughly 100 years, against a universe that is 13.8 billion years old, on a planet where complex nervous systems capable of even noticing a signal have only existed for something like 600 million of those years. If there is a civilization out there even a single million years further along than we are, a blink of an eye on any cosmic clock, the gap between their tools and ours might not resemble the gap between two nations running different radio standards. It might resemble the gap between two forms of communication that don't share the same physical channel at all. We are listening for radio waves because that is the technology humanity itself is still in the infancy of. We only recently learned how to encode a single unit of quantum information onto a photon, stop it dead inside a cloud of ultra-cold atoms, carry it physically to a new location as matter, and read it back out as light with nothing lost. We don't yet have instruments capable of detecting a quantum channel like that across any meaningful distance. We can barely hold one steady across the length of a single laboratory room, let alone across the light years separating one star system from its nearest neighbor. Now I want to be careful here because there is a boundary that physics genuinely does not let anyone cross, no matter how good the story sounds. Quantum entanglement is real. It has been confirmed again and again under increasingly rigorous conditions, and it is, in a strict technical sense, non-local. But it cannot, under any interpretation the mathematics allows, be used to send information faster than light, or to send usable information entirely on its own. The correlation between two entangled particles only becomes meaningful once it's compared against an ordinary classical channel, the slow, familiar, light speed kind. So no, entanglement by itself isn't some secret alien telephone line humming quietly overhead, and it would be dishonest to let this story imply otherwise. What the physics does leave open, carefully, is something narrower and in its own way stranger. A mode of encoding and moving information using light and matter together, the way Howe's lab did, that has no true classical analog, and that would be functionally invisible to a telescope built to register nothing but raw electromagnetic intensity arriving from far away. Not hidden, not disguised, simply never broadcast as the kind of signal our current instruments happen to be built to notice. That single reframing changes the whole shape of the question. 60+ years of silence was never actually proof that no one is out there. It was only ever proof that our method of listening rests on one very large, very old assumption: that anyone advanced enough to build a transmitter would still be transmitting the same way 20th century humans happened to figure out how to. So go back for a second to the silence we opened with. What if it was never an ending at all? What if it was never even an absence? What if it's the sound of a conversation already happening on a channel we simply haven't built the ears for yet? Here's what I keep coming back to. Thinking about a small laboratory in Cambridge where someone once held a beam of light so still it forgot which way it was supposed to travel. If the silence out there isn't evidence of absence, but evidence that we built the wrong kind of ear, then the fix was never going to be a bigger radio dish pointed at more of the sky. It was always going to be a stranger, more patient kind of instrument, closer in spirit to the careful, quiet machinery sitting in that Cambridge lab than to anything humanity has launched into orbit so far. So here's my actual question for you, and I mean it honestly. If you had to guess what we should be building next instead of another radio telescope, what would it be? Put it in the comments. I do read them, and I genuinely like to know where you land. If this kind of story, real physics, honestly explained, pointed at genuinely open questions, is the kind of thing you want more of, the subscribe button is right there, and it costs you nothing while doing a real amount of good in getting stories like this one in front of more people who'd enjoy them. And if you know someone who still looks up at the sky sometimes and wonders the same things you've just spent the last few minutes wondering about, send this their way. Their assumptions could probably use the same gentle bending yours might have just gotten. Because somewhere out there, or maybe nowhere at all, the universe is either speaking in a language nobody here has learned to hear yet, or it really is exactly as empty as it sounds. And right now, honestly, not one physicist, not one telescope, not one published paper anywhere on record actually knows which.